friends, this is Dr. Siva Nagaraju, Associate Professor from IARE. Today we are going to discuss the detection of FM waves. So we are going to detect the original message signal from FM waves. Okay. So coming to the topic, frequency demodulation is a process of recovering the original modulating wave from the frequency modulated wave. That means in transmitter where modulated signal is generated and transmitted the channel. At the receiver, we are going to recover the original message signal from that modulated wave. So FM demodulator is basically a frequency to amplitude converter. That means we can think like that. This is FM demodulator. So for example, here we're having different frequencies that is coming. This is FM modulated wave. So here we convert this frequency to amplitude converter like that. So FM demodulator is basically a frequency to amplitude converter. Now these FM demodulator having two varieties. One is direct type and another one is indirect type. Again, this direct type is classified into two varieties. One is frequency discriminator and another is zero crossing detector. Whereas in indirect type, we're having a phase lock loop and Foster discriminator type also there. So in this session, we are going to discuss about the frequency discriminator, zero crossing detector, and phase lock loop. Okay. So what are the requirements for this demodulators? So any demodulator can fulfill these requirements. So the first one is it must convert frequency variations into amplitude variations. And second one, this conversion must be linear and efficient. And the third one, the demodulator circuit should have insensitive to amplitude changes. It should respond only to the frequency changes. And the last one is it should not be too critical in its adjustment and operation. That means the operation is simple. So these are the requirements must fulfill by the demodulator. Okay. So this is a block diagram for this frequency discriminator. Here we're having two slope circuits and two envelope detectors, and finally having a summation. So the output V0, which is equal to V01 minus V02. So we're getting output at this summer. Okay, so this is the block diagram for this frequency discriminator, and now you can see the circuit diagram. So in this circuit diagram, we're having two slope detectors and one center tap transformer and some filters having. So the input transformer having a primary winding and also secondary. So the primary tuned circuit, which is tuned to the intermediate frequency, that is FC, where the secondary upper tuned circuit, which is tuned above FC, that is FC plus delta F. Whereas the secondary tuned circuit, which is tuned below FC, that is FC minus delta F. Okay, so this is a description about this circuit diagram, and now we can see the operation, how this working operation is done. So basically in this working operation we take three regions. One is Fn, which is equal to Fc, that is the input frequency, which is equal to the current frequency. So at this region, the induced voltage in the T1 winding of secondary is exactly equal to that of induced in the winding T2. That is, already we've seen that circuit diagram having a secondary winding has two parts. So the first one is a T1 and the second one is a T2. Okay, so thus the input voltages to both diodes D1 and D2 will be the same. Therefore, the DC output voltages V01 and V02 will be identical, but they are opposite polarities. Hence, the net output voltage is 0. Already we've seen that in the block diagram, V0, which is equal to V01 minus V02. So both are having the same voltages, then the net output voltage is 0. And the second region is Fin is greater than Fc, or Fc less than Fin less than Fc plus delta F. That means the input frequency is in between Fc and Fc plus delta F. Or simply, the input frequency is greater than Fc. So in this situation, the induced voltage in the winding T1 is higher than that of T2. Therefore, the input to D1 is higher than D2. So the positive output is getting from D1, which is higher than that of the negative output of D2. Therefore, V0 is positive. Why? Because V0 which is equal to V01 minus V02. So V01 is higher positive value than the V02. So we're getting positive voltage. And whereas the third case, that is Fin less than Fc. So in this case, the induced voltage in T2 winding is higher than in T1. So input voltage to diode D2 is higher than that of D1. Hence, the negative output V02 is greater than V01. Therefore, the output voltage of the balanced slope detector is negative. So we're having the three cases. In the first case, we're having the zero output. In the second case, we're having the positive. In the third case, we're having negative. So here you can see in graphical. So Fin, which is equal to Fc, having 0. And Fin, which is in between Fc and Fc plus delta F, having positive. And the third one is Fin less than Fc. Okay. So the useful range, what is given here, is in between that line. So there is a slope. Okay. And another one is a zero crossing detector. The zero crossing detector operates on the principle that the instantaneous frequency of an FM wave is approximately given by Fi approximately equal to 1 by 2 delta t, where delta t is the time difference between the adjacent zero crossing points of the FM wave. Okay. So this is the wave, what you get in the FM wave. So how many zero crossings is we're taking the count, and delta t is taken as 1 cycle peak. So the time t is chosen such that it satisfies the following two conditions. One is the time interval t is small compared to the reciprocal of the message bandwidth w, and another one is the time interval t is large compared to the reciprocal of the carrier frequency fc of the FM. So these two conditions we must follow, and let the number of zero crossings during interval t is defined by n naught. Hence, delta t is the time between the adjacent zero crossing points is given by delta t, which is equal to t by n naught. Already you seen that picture. So we've taken delta t time and total t. So in that total time t interval, how many crossings are taken? It is n naught. The instantaneous frequency is given by Fi, which is equal to 1 by 2 delta t. Therefore, the instantaneous frequency approximately equal to n naught by 2t. That means we are going to substitute this delta t value, then you get this one. So this is a block diagram having to generate or to detect this message signal by FM, having limiter, pulse generator, and finally integrate. Okay. Now the limiter converts the input FM wave into the corresponding square wave. The pulse generator produces short pulses at the positive going as well as negative going edges of the limiter output. Averaging of these short pulses over an interval t is performed by the integrator, the output of which reproduces the original modulating signal. So this is the way we have to find the original message signal. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.